Thanks, Tom. And as Tom mentioned, I am the only person not from Unity. And I'm also one of two people. There's a guy back there with a Dell as well, but I'm one of two people here that doesn't actually have a Mac, so sorry about that. Just go ahead and, let me just get this started here. Well, while I'm rebooting, let me quick give you a little bit of intro about myself. Couldn't resist it. So actually, the UAC thing is, anyway. So I'm Matthew Wegner. I'm from Flashbang Studios. We are a 3-person team with some 2 other people. We're kind of spread out this day because yesterday we were all kind of clustered together and didn't really work with networking. We make small web games. Right now we actually made Sploom. It's one of the top dog finalists. So let me have Steve quick show you Sploom with the darkest magics of wireless. So yeah, just take it away. So Sploom is a small web game. We made it in 3 weeks, but what we did was, and I have a big interest in physics games, we basically took Puzzle Bobble and added physics to it. So in the same way that other games have done this, where they've taken breakout games and made it very physical, we took Sploom and took Puzzle Bobble and made it very sort of physical-esque. Of course, the problem is when you work with physics, you need to find a way to make it tuned well. It's really easy to slap physics onto a game, but it's really difficult to make it feel like it's actually satisfying. It's not glitchy, it's not too fast, it's not too slow. And we have a nice little ticker, which is kind of freaking out there in the bottom. So we have all these levels, and they're all based on physics. So that's basically Sploom. We'll have it online. We still have a few bugs in this version because of the contest deadline. We haven't updated it yet. But this will be online with the 2.0 web player probably later tonight at the URL up there. So all right, go back to PowerPoint. Should probably close that or change. So that is Sploom. We are one of several finalists. I think all the finalists are here, right, or not? There's 2 over here. Anyway.
It's not here. Grabball is not here.
OK. Everyone but Grabball, which is pretty sweet. I also run a website called Funmotion where I talk about physics games. Most of these games are on PC, but about 10 of them are currently on Mac. So Funmotion is basically a review blog. I take games, I write about them. I have 50 or 60 games, and they're games like Gish or Bridge Builder or Ski Stunt Simulator, games that are basically pure physics games. And I'm going to talk a little bit more about how to add physics to other games and not games that are based entirely on physics. So for each review, I have screenshots. And then I also make a video capture for each review. So even if you can't play these games because you're on a Mac, you can still go in and check them out, see what they're like, and get some ideas for putting physics in your games. And I put quirky little music on it because, well, I can. And I'm also one of the co-directors for the Independent Games Festival and the upcoming Independent Games Summit. So if you have any questions about the IGF or the IGS, feel free to talk to me, or Steve is the other co-director. But today I'm going to talk about physics. And one of the things that when I started thinking about physics, I started looking back at physics in general, not about just physics and games, but what I've enjoyed about physics. And I remembered that one of the things I really liked to do when I was a kid was to throw balls up on my roof. We had a standalone garage, and I would throw tennis balls up on the roof and then watch them bounce down. And then I would put other objects on the roof to make obstacles, and then throw a ball up there and then watch them bounce down. And this was really fun to me when I was a kid. And in fact, the game plays a lot like Peggle, which is it out on Mac yet? I've revealed myself as totally ignorant of Mac stuff. So this is actually a scan from my photo book as a kid. When I was thinking more about physics in general, I thought a lot about what I did as a kid with physics. And this is kind of my childhood. There's all these physical things and a tiny goat. That's actually from the scan from my childhood. And then today, I do a lot of things that are very physical, too. This is me unicycling. And I know Forrest also unicycles. But this talk is not going to be about physics in a very technical term. It's going to be about physics, and with apologies to Aris for using one of his screenshots. It's going to be about physics in the more philosophical term, about what is fun? Like, why is this kid having fun with physics? And how can we make that kind of fun apply to video games? So in physics, in real life, many of the things that we do for competition or for fun involve physics. Indeed, a lot of the sports are simply about physical navigation. Some sports do include physical endurance or physical ability, but most of them are about the physical interaction and about the fun of doing things physically. And as adults, we still pursue these unique physical experiences. We go skydiving or we go river rafting. This guy is totally, this guy here is totally about to eat it. So what I wanted to think about was not how to tell you this is what dampening does. This is, if you modify dampening, this happens. This is what a mass of an object is. Because it's really easy to go into the docs and just to see, OK, well, mass is the mass of an object. And it's really easy to make a test case where you just modify the mass in your little test case and see how it behaves. So I wanted to talk more philosophically about how do you approach tuning the physics system and how do you apply whether or not this is fun to that tuning. So I wanted to take my childhood fun of jumping off really, really high objects and sort of transmute it into the other thing I enjoyed as a child, is sitting there and playing video games. And my mom wrote that on the picture, by the way. Forever branding my, I don't know why we had the TV so high up either. It didn't. So, and indeed, with physics in video games, one of the first things people did was they just took what we did in real life and put it into a video game. So we have games that are about the physical navigation of objects, like driving. And we even have games that are more about the physical endurance aspects, but obviously, to play a football game, you don't need to be in shape. And the mini games do just add physics. A lot of first-person shooters just add a bunch of crates to games to make it a little bit more embellished, a little bit more enjoyable. It's actually from the Onion's article about the crate game. But what's interesting to note is that even in the direct one-to-one, let's make this physical activity into a video game, there are still a lot of things missing. Like there's no real fun skydiving game out there. Or there's no game just about unicycling. And Uniracers does not count. Those are the guys that did Grand Theft Auto eventually, by the way. And even like the small, really quirky physical stuff we used to do as a kid, there's no game about a water balloon toss, which would be a really awesome game. So I leave that up for a second. So the question with this talk is, as we sit down to actually build these things, as we actually sit down to build a video game, how can we incorporate physics in the same way that we enjoyed physics as a child and we enjoy physics as humans? How can we incorporate the newer games? And more specifically, how can you, the audience, incorporate these things into your games? So I'm making an assumption here, probably a safe one, that we're all using Unity now. And one of the things that Unity tries to do, at least in my opinion, I can't obviously speak for the company, but they mask complexity, unneeded complexity. So if you have to modify dampening in your physics game, you don't need to do this. You don't need to read a paper on how to apply dampening to your physics simulation. What Unity does is they expose what's essentially a knob. So they have a little, hard to see that on the projector. They have a knob for dampening. This is value that you can change from 0 to 1 or above 1 to modify dampening. Of course, the problem there in the engine is that they have all these knobs. So how do you tune them all? It's really easy to change one particular thing. You can change whether or not it's being dampened, whether or not its angular velocity is being dampened. But how do you adjust all these knobs so that the game is fun? Well, before I get into the specifics of tuning a physics system, I wanted to talk about the philosophy of tuning any system, whether it's even like an audio system. Like how do you make, if you're a sound mixer, how do you make the song sound good? How do you make sure there's enough bass, there's enough lead vocals? And how do you tune any system, whether it's a damage difficulty system, the physics system, or any other system in your game? So I wanted to talk a little bit about that first. Yeah. So I think the first thing to do in tuning any system is to very clearly understand what it is you're trying to reach. And in physics, this is mostly imagination. But in any other system, like let's say you want to have a really bassy song when you're doing like a sound mixing. You should have a very clear example of what you're trying to accomplish. So pick your target, and then just as clearly as possible, imagine how the system should behave, what it should look like. Because when you actually go in to tune it, you're going to have all the pieces there, but they're not going to be in the right order. So you're going to have to assemble, essentially, the entire system together. And even if you have a clear target in mind, and when you have all the pieces there, you might get sort of led astray. You might end up tuning things, and you end up with not the actual vision you had in mind because it's a 2-week process. And in those 2 weeks, you've gotten very distracted by other things. And the corollary to that is don't tune early. It's kind of like if you had a very clear picture of what you wanted in mind, but you didn't have the proper puzzle pieces to do it, you're never going to be able to assemble that puzzle. So if this is your target, this awesome rainbow scene, but all you have to tune is a bunch of grayscale paints, even if you tune and tune and tune, you're never going to be able to reach the actual target you have. So if you want to have a very bassy song and you're an audio mixer, but you haven't recorded the bass track, you're going to be in trouble. It's going to be really hard to add bass to your track. And in physics, sometimes this usually means you have the wrong joint setup. If you're trying to make your joint setup behave a certain way, but you're using the wrong joints, it'll be really, really difficult. Like if you're trying to, also on wheels in a car, apply friction to actual physical objects, that might not be the best way to make it actually grip the ground. You might have to use like a wheel, wheel collider, like a raycast system. So the next thing in tuning is to establish your critical path. What needs to come first before you can tune these secondary things? And a lot of the times, especially in game development, I liken it to a stack of soda cans. There are certain cans that have to go on the bottom before you can put the other ones up. But the problem is you don't know which is which. So when you're learning something or tuning something, to get A working, you have to get B working. To get B working, you have to get C working. But to get C working, you have to have A working. And there's this interconnected mess of stuff. So you have to make sure that you can identify, well, if we can get this stuff balanced, then we can worry about balancing these sort of corollary things. Because if you don't get it right, then obviously you end up with, I can't believe someone put that in their apartment. But, so I mean, a lot of this comes down to planning. And planning is more of a system decision than it is a particular physics or tuning decision, because you want to end up with something like this. You want to end up with a very good system. So in Splume, with our little balls, we ended up having, for instance, we added the eyes much later. And the eyes had to know, well, which balls are currently active. Like, which balls should they follow? Should they look at the balls that are coming up or the balls that are the arrow position? So in our architecture, we had all these. Steve's moving the mouse around because it's still connected to this. Here, you can take it back. So in Splume, we had to make sure that we had planned ahead in our architecture so that we could have pieces understand where other pieces were doing. And this does matter in tuning. So for instance, our next game may or may not be about hunting down raptors with a Jeep. And the raptors are going to have to know which Jeep is closest to them. What direction is that Jeep going? Because if we wanted to add all this stuff into the system later, and we haven't planned for it, then it looks a lot more like this. We have all this stuff that's interconnected, and it's not a very good architecture. So when you're tuning a system, make sure that it's planned well and planned well for tuning. All of your variables are exposed. It's really easy to go in and change a bunch of numbers. So now that you have all that stuff in, it's actually time to tune a system, to actually start plotting points. So what usually happens when it comes time to figure out how all these knobs should be set is you just start throwing darts. You basically, so let's say we have some system where we're trying to tune anything. And we're changing the number, whether it's dampening, the difficulty, the speed of an enemy, whatever it is. So you start out by just picking the number, like maybe 2 would work, 1.8. And then you have to assign some sort of response to that number. You have to decide, let's say we're tuning the damage system, and it's too easy if the damage is 1.8. So what you do next is you increase the number to some arbitrary amount. You just sort of throw a second dart and say, well, let's try 7.5. Then you have to rate that. And I'll talk later about how you rate the feel of a physics system. And then what you end up doing mentally is you try to interpolate between the two. So if that's 1.8 and that's 7.5, then obviously some number in between should theoretically be some experience in between the two experiences. So you end up sort of defining where in the experience graph you actually want this number to land. And then it turns out that in this particular tuning example, maybe somewhere in the 5 range is kind of the number that we're looking for. But one of the problems with this technique is you have to mentally interpolate between the first dart and the second dart. So you end up with all these mental interpolation errors. So let's say that we're tuning the speed of a car, and the speed of the car comes out that it's way too slow. And the second dart is that it's way too fast. So you might mentally interpolate linearly between the two and say, well, let's just take all the values that we've used and do a midpoint. But the problem is sometimes that can create nonsensical results. That might not be what you're after. Proud of myself for finding that image. You actually might want an animal in between that's a completely different animal that wasn't just the midpoint of all those numbers. And the problem with physics is that sometimes the graph between the two might look like this. And this is even true of single number graphs. In Splume, we have these objects that actually act as the hinges, that are separate rigid bodies. And as we increase the mass and lowered the mass, the behavior went up. And then as we increased the mass, it became really heavy. But as we lowered the mass to very small numbers, it actually became really heavy seeming. So the graph actually wasn't this linear line between the two. It was kind of like this weird little spike in the middle. So if you're tuning multivariable systems, like if you have a racing game where you have a really fast car and a really slow car, you really just can't pick the steering values, the engine speed values, the mass values, and just pick the midpoint between the two to get a car that behaves somewhere in between. And part of the problem with doing multivariable stuff or just even plotting points like this is the problem of local maxima. So let's say that this is our graph of how things actually behave. And we've picked the little green dot there to start with. So we say, well, this is only OK in our experience. We've rated it somehow on the red graph. So let's make it a little bit higher or a little bit lower. So we change the value lower and we say, well, the experience has gotten worse, whatever we're rating it by, difficulty, how fast the car seems, how responsive it seems. So you end up going in the other direction. Oh, and it seems better. So you end up increasing the number yet again, and now it seems worse. So you're convinced now at this point that this middle point is the best number for your system. But obviously, if you can see the larger graph here, this is actually much higher than that. So when you're plotting points, be careful of zeroing in on this must be the correct number, because it might be that if you had tried a number way out of range in either direction, you actually might have found a hill that was much higher. So just to recap, in tuning any system, just make sure you have in mind what you're trying to accomplish. Like, talk about it with your team or your partner, or even if it's just yourself, then write it down. Like, I want the car to behave like this. I want it to feel like this. Try to come up with as many words as possible to describe how you want your physics to feel before you start changing numbers. Because then, if you stumble across what feels good, it was just by chance. It wasn't by any intent of your own. Don't tune early. Make sure that before you start changing the mass of your object that you have all the hinges in place, all the joints in place, all the other objects in place. Or you might not be able to accomplish your target. Figure out which to tune first, and I'll talk about that in the physics section, which variables you should actually get locked down before you start changing other variables. Try to plan as much as possible. Obviously, it's very difficult to plan for all circumstances. But I mean, do your best in planning. And then when you're plotting points, just be careful of local maxima. And try to make sure that your numbers are actually not, just try random numbers. Try really, really high numbers and really, really low numbers to make sure that you know which number you're changing, how it behaves. So now to talk about video games. There's actually a valid line of criticism there, but anyway. So physics in games. Who here has added physics to their game with Unity or plans to in any significant way? It's about half the room. So the one thing that I think is really key in physics in games, and this is an extremely obvious point, but I think it's so obvious that we often overlook it. But in physics in games, we view everything, everywhere, through the prism of our own experiences in life. So obviously, we live in a physical environment. When we play a video game, we're going to look at it and compare it to the physical environment of real life. Again, an extremely obvious point, but I think a lot of people forget about it. We identify with everything. So when we play a video game and we see a car, we identify with, well, I know what cars are like in real life. It should behave this way. So let me give you an example. So this is a test from a previous talk I gave, but it's a bunch of clowns falling down the stairs. And this is kind of immediately fun. It would be fun to play this game, and there have been ragdoll games where you push people downstairs. But we can actually identify with it. If you were to make mouth sounds as he falls down the stairs about how much pain he was in, you can see his head hit, you can see his leg hit, you know how much damage each clown probably should have accrued. You can identify with it in a very, very strong way. He's kind of standing out of the way, these guys back here. But in this example, how much damage is this object accruing? And what's funny is if you actually try to observe your own observations of it, you realize that you're trying to anthropomorphize it. You're trying to say, that's his head, that's his arm. Oh, he just hit his joint, that's his leg. You're actually trying to identify this sort of random collection of joints and constraints with you as a person. You're trying to apply your experiences to it, which is, again, a really obvious point, but I think if you're conscious of it, it's a very good thing. So in video games, this kind of falls on a scale. There are some things where it's very informed by real life. Obviously, in a realistic racing game, quote realistic, it's informed. These cars should behave like the Shelby should behave as a Shelby behaves. But as we get lower on that scale, we start to become more informed by real life and less dictated by it. So in Mario Kart, obviously, the heavy-looking car should behave in a heavy way, but that doesn't mean that I can't go from 0 to 60 in like a second. And then as we start going down the scale, we're still informed by things. Like in Mario, I just kind of use a lot of Mario screenshots. We're informed by this. Mario should behave in a certain way. There's obviously some sort of gravity here, even if it's circular. And there are certain things Mario should be able to do and shouldn't be able to do. But again, those things are solely based on our experiences as living, breathing human beings. And then as you go even farther down the scale, this is Gish. You play as a 10-pound ball of tar. It's a little bit less informed. How should a big ball of tar behave? And what's interesting to note is they actually added eyes and a mouth to him as a means to identify with him. So when he gets in pain, if you do something that causes him pain because his springs are too close together, which might not be obvious to you as a player, he grimaces, which is obvious to you as a human being. So in Sploom, we actually did add eyes later on, even though it's part of our initial concept. But Sploom is even less informed. I mean, how should these objects behave when they stick together? Should they be really springy? Should they be really, really heavy? Because I can't think of any situation in life where there's a bunch of objects that are thrown and stuck together. So when you talk about physics in games, the customer, the player, is going to expect something. They're going to expect the car to behave a certain way. They're going to expect Mario to behave a certain way. Even if you have a very abstract game, what's interesting is they're going to expect that to behave in a certain way. So they're going to pick out the experience that they like the most. So how do you make your physics experience in alignment with what they want as a player? Well, when a player plays a game, like a skateboarding game, they want to be able to skate like Tony Hawk. They want it to be easy. They want to easily experience awesome skating. But they also tell you that they want it to be realistic. They don't want it to be realistic in the way that you need to practice for 10,000 hours and have an aptitude for it. But they want it to be realistic in this weird abstract way. So what does it actually mean when they say they want it to be realistic? They don't mean they want to skate in the game as they would skate in real life, because that would end up like this. They mean they want it to be realistic in a way that it seems like they're skating like Tony Hawk, but without having to actually skate like Tony Hawk. So if you had a flight simulator, and you had to do a pre-flight, where's our Sean? Our intern actually likes air traffic control games, which I discovered last night, which kind of disturbs me. But mostly in a flight simulator, you don't want to have to do a 1-hour pre-flight check. You don't want 10,000 hours in the cockpit to be able to fly. It's this weird balancing act of the player wants it to be realistic, but they don't want it to be too difficult, too much like reality. And what's funny about balance is the reason that we can't provide this experience is actually because of the inner ear. So when you're in a NASCAR cockpit, they have all these gauges there that you probably don't have. But I mean, for the most part, all of this stuff can be represented. You can buy a steering wheel. You can buy even a seat. You can buy cables or pedals. But what you can't do is you can't have your inner ear. So the fidelity of the actual experience of driving NASCAR is highly dependent on the fact that they have an inner ear. They can feel to very subtle degrees which way the car is moving, if the wheels are slipping, what's actually happening there. And when they're playing the game on the couch, they don't have any of that. So to compensate for this, you actually can't provide them a simulation that's one-to-one with reality. And if you did have a simulation that was one-to-one with reality, you would require the exact same level of skill that a real driver would require, which is obviously not what they want. They don't want to sit down for 10,000 hours and learn how to be a NASCAR driver, with rare exception. Our intern also likes NASCAR. So there are two ways to approach this as a designer. One is just to dampen the simulation, to slow everything down. There's actually a guy diving for cover there. I didn't realize that. So that's one solution that we often take, is we just take the simulation and then we just start applying dampening values so that the player has more time to react to things. The other option is just to simplify the simulation. Instead of the actual NASCAR car, now you have a simplified series of controls, simplified behavior, very arcade-style physics. So what other metrics can you apply to the physics balancing? When you're actually going in to balance the physics system and you've sort of set aside, well, this is how realistic it's going to be, how do you actually balance other things in physics? Well, one thing that we spend a lot of time on is just the timings of things. Like in Sploom, when two balls connect, what should the recoil length be? How do you control it? And we actually spend a lot of time, even on our other projects, with changing how fast and small things scale. So how long is a recoil? How fast do things take? I mean, you should actually identify how long it would take to get up a hill. How fast does it take to stop in your racing game? So one way to worry about time is just imagination. I actually, when I sit down to work on a game like Sploom, I try to imagine in my mind what it looks like to connect two objects together. So then when I'm actually tuning the numbers and it feels like it's too sluggish, it feels like they come to rest too quickly, I'll actually work on, well, we should lower the dampening values. And in Sploom, I actually had this very mental target of how long it would take to stop moving. And it was like 2 recoils. So when you had a heavy object connect, it just swing up, swing down, and then stop. And one way that I try to accomplish this when I'm actually sitting there fiddling with numbers is just mouth sounds. I find mouth sounds to be a very, very good way of doing things. So I'll play the game before we have any sounds in, and I'll just make sounds as I'm playing the game of like little popping noises, little connection noises. And the mouth sounds usually last about as long as I think it should last. So if I have a mouth sound and then I can figure out, okay, it needs to be this quickly of a stop, then I can try to make the game match up with my mouth sounds. But one of the problems in physics especially, or any system, when you're tuning numbers, is maintaining perspective. So 2 things are happening when you're playing a game that you're also designing. The first thing is that you as a player are adapting to the system. So if the game has very clunky controls or it's very sluggish feeling initially, what you'll do as a player is you'll compensate for that. So 2 hours after playing the game, you might think it again feels normal. You've normalized the experience to the point where you think it's fine. But at the same time, as you're playing the game as a developer, you're trying to adapt the game to the player. So while you're adapting to the game as a player, you have this experience in mind of how it should play, and you're trying to make the game numbers change to match up with that. So let me give you some examples of this. So one is this picture. It actually takes a second to realize what this picture is. Pretty soon you realize, okay, it's a tunnel. Okay, those are reflections. It takes a second for you as the viewer to adapt to what the designer has intended. So this is the proper way of doing it. There's a very clear intent here, and you as the player have to adapt to it. The other example is people or dogs that just get really, really muscular in really, really weird ways. And what's happening here is that they have at first a vision in their mind of, I want to be muscular, I want to be strong. And they view themselves as very broad-shouldered, thick muscular legs. But the problem is, it takes a really long time for them as the designer to accomplish this goal. So as a player, they adapt first. So they adapt to their new view and say, well, this is normal. I need to get bigger chest. And then they keep doing these things until you see people walking down the street that are just completely out of alignment. They don't look good. They look freakish, which is what I want to own that dog. So the problem here is that it took a really long time for them as the developer themselves to accomplish their goal in mind. So them as the experience, like as the viewer / player of that experience, they adapted first. This is also the same phenomenon that causes really, really bad hair, is that people lose track of what they look like. I don't know if you ever had really, really bad hair, and then you look at a picture of yourself, like 2 years later, and you said, did I look like that? Like, why didn't anybody tell me? But the problem was you were adapting to that experience and normalizing it. So when you're designing a physics system and changing numbers, it's very easy to adapt to the system you're trying to change, and then you lose all objectivity. So after a while, you actually can't trust yourself. You can't trust your judgment on a game. You think it feels right, and everybody else is telling you, no, it's sluggish. It actually might be sluggish. So one option is just to come back to the game 6 months later. But if you're working on it and you have a deadline, obviously you can't. That was my deadline sign. I missed it. So one option there is just to get other people or dogs to play your game. So testing also breaks away a little bit from physics in that there are a number of ways to test. And I think Sam is the resident testing expert. Tell me if any of this is totally out of alignment. So testing metrics. How do you apply tests to physics games? Well, the first thing you have to do is you have to totally pick apart the game. You have to be open to rough criticism. If you have a bunch of players come in and play your game, you should be willing to take a little pain. And you also need some objective measurement. You actually need someone to play a game. Maybe you're recording how long it takes to beat the level. And you say, well, our lap time is 2 minutes. Your lap time is 4 minutes. Something is wrong here. But you also need some subjective way to actually play the game. As your players are playing the game, you want them to vocalize their subjective experiences. So here's a little example. Sam, how many windows are in your house?
Let's say 7.
Okay, well, actually think about it. Is it 7? I actually need you to think about it for this little example.
I'm thinking. 9. 9 total.
Okay, 9. So 9 is an example of if you ask the player, did you have fun? What did you think about the car? And they said, I didn't have fun, or it was too slow. That's a very singular number. So how did you come up with 9?
I actually thought about the layout of the house,
okay,
which walls had windows and where.
Yeah, so you actually walk through each room in the house, adding them up. So that's the process you went through. And when you're getting testing from players, you want them to vocalize the process. If someone's testing if the game's fun or not and they say no, that's not very useful. But if you can get them to vocalize the exact same process as Sam just did, we actually have testers sometimes go through this and say, okay, when you play the game now, tell me the process as you just did for the window. So then if you get them to vocalize, it wasn't fun because I thought these two pieces were connected, but they weren't. Or I tried to turn here and I thought I could make the turn and my car flipped over and I thought it shouldn't have. Or I thought I could make that jump at the current speed, but I didn't. That's much more useful in testing physics games than if they just said, it's too slow, it's too hard, it's too fast, or whatever it is. The other thing that you want to do when you test people is you want to give them some sort of variation. It's hard to have one tester play 4 different balancings of the same game, 4 different numbers of this car is now a lot faster or a lot heavier. But it is possible to have a couple of different subtle variations and try to ask them which one did you most enjoy. The other option is to, instead of these number changes where you might have the same car rig, but it just has different mass and dampening values. The other option is to have a bunch of different variations, like more than just number changes, actually structural changes, and then just have them play it and try to figure out which one players enjoyed most. So now actual physical variables. A lot of these are in the docs. I didn't want to talk too much about what dampening was and what it meant. So when you're actually going into to tune a system, we have the Y-graph kind of covered now. We have ways to assign or determine if the physics game was fun or if it was too sluggish, or how to get that feedback from a player. But on the X-graph, like what numbers can we change back and forth to try to accomplish this goal? Like what toggles and sliders and buttons do we have in the physics system to actually try to meet our goal of a racing game where it's really carving, or like you have a jet ski game and you want to make it so you can feel like you can carve in and out of the waves. Well, what would you actually change to make that accomplished? Well, the first thing in physics that you have to really worry about is scale. Because scale is actually absolute. Many of the other numbers are relative. It doesn't really matter if your objects are a mass of 10 and a mass of 100, or a mass of 100 and a mass of 1,000. That's the same ratio. But scale is not. So here are two objects. One is the USS Enterprise, the battleship, not the starship. And the other is a tennis ball. So if you actually had these two objects on screen at this size and dropped them in a gravity of 9.8 meters a second, the USS Enterprise is about 300 meters long, and I said that was about 0.6 meters, which might be like 100 feet. I don't really know how the metric system works. So this is the function to determine how long something falls. So if you actually drop these two objects in your game screen from here to here, it would take way less than a second for the tennis ball to drop, but 14 seconds for the USS Enterprise to drop. And this is because gravity is constant regardless of its size. So if you import all of your objects, and all of your objects are 100 times as big as they should be, they're going to feel 100 times more sluggish. So when you're working with physics, the first thing to do is just to make sure that you're modeling to scale. Make sure that your humans are like 1.6 meters tall, that your cars are actually car-sized, and otherwise you're going to end up in a lot of trouble later on if you realize that, holy crap, our stuff is 100 times as big, and we just set up a bunch of stuff in our physics engine. So the other thing to tune next is mass, and mass is more relative. It doesn't really matter to the engine if a mass is 10 to 1 or 100 to 10. But you should start identifying, well, how much do things actually weigh in real life? The easiest thing to do in physics is to try to model to reality. So a car should weigh this much. A space shuttle should weigh this much. The engine gets a little wonky if you have a game where you have a tank and then you have a bullet. That mass differential is going to be a little bit strange because the bullet will always be able to push the tank just a little bit every collision. And then the thing with mass is that you should tune it so it's relative. And the danger there is you actually can tune relative to itself. If you think about a guitar, which this cat is totally rocking out on, if you have a guitar and you tune all the strings relative to each other, you can actually play a song that sounds about right. But the problem is then you can't play in a band with that guitar because if you have other guitars, they're totally out of alignment. So just be wary on the fact that you can tune mass relative to each other, but then if you bring in new objects that have different masses or like another system that's relatively tuned, they actually might not be able to combine. And the next thing is dampening. Now dampening is one of the things that you actually want to change quite a bit. Dampening is a way to make a system more stable, especially if you have a lot of joints that are connected, you'll get a lot of really wonky behavior. Actually, I should probably just show Sploom. I think I have time. Steve, can I steal the laptop? So while Steve's unplugging the laptop, the thing with all these tuning systems, you actually want to tune by states. That's the best way to do it. So you should have some state logic that says if our object is in the air, we should tune it differently. Or if you have a car that has really, really heavy dampening and you get into a crash where the player can no longer control that car, it makes sense to turn off all of the dampening so the car starts to tumble in really crazy ways. So you should have states in place where your game logic knows if an object is connected or if it's in the air or if it's completely something else. You actually can tune all these numbers by state. So let me just show you some of the numbers in Sploom. So let me show you one of the levels. Sploom here. This mouse is freaking out. Oh. So in Sploom, a lot of our levels had a lot of really heavy physical things. Reveal that I know nothing about Unity. So we have these levels that have really physical objects, and the problem here is that a lot of these levels are based on the physics that we had. We actually changed the physics balancing after we made a bunch of levels, and then actually broke all the levels. So like you can break these things and they spray apart. This is one of the levels that doesn't work in the current web version. Okay.
That was the one that was there.
Which one is the snaky? Snaky McSnake? Our awesomely, cleverly named levels. Hold on. So we have all these things that are really highly dependent on how the physics actually behave. And this is nothing like Puzzle Bobble at this point. It's just like a crazy physics test. Die, snake. I missed a bunch over there. But anyway, but I wanted to show changing some of these physics variables to give you an idea of what happens when you turn off things like dampening. I can see my tiny little thing. is what happens when you make a project in like 2 or 3 weeks. Click the fireballs. So this is our default dampening. What we wanted it to be was stable enough that it felt more like Puzzle Bobble and less like a crazy system. So you can see when you fire a new piece in, it'll recoil and then pretty quickly come to a stop. Like you actually can tune very, very, very easily how much it actually comes to a stop or not. And it's stable enough to the point where you actually can just spam balls like a crazy man. Uh-oh. Oh, shit. So if you turn off all of the dampening, let me see if I can figure out where to do that in this tiny, tiny window. So we have dampening in a couple places. We have a hinge joint. Actually, let me just show you the hinge joint system. God bless Unity. So when we have all this stuff set up, oh, you can't. Hey, where's Nicholas? Drag select, please, in the 3D view, like drag select multiple objects. Our artist really, really wanted that. Just thought I'd point that out. So we actually have all these hinges that are made between the balls. And what we actually did was, instead of connecting the balls together, there's actually a third object that's created in between the balls. So like on these two objects, there's actually a third rigid body right there that actually has 2 hinge joints to each other object. And we did this for some convoluted reason that we actually didn't end up using. But what it allows us to do actually is change the balancing quite a bit. So with one toggle, actually, let me show you where that is, if I can find out where Steve's scripting is. I actually edit my scripts on a Windows box because I'm a total rebel, so sorry about that. Where's lock rotation? It's in here somewhere. Should have prepared this more. Oh, there we go. So we actually could completely control the fact that you can turn off any, let me refresh. You actually can turn off any kind of bend at all in the system, which is something that we didn't quite expect. So now we can actually do this thing where if you build sideways like this, it actually won't bend at all. So you can build these, should pick a level that has more colors. So you actually can build these things that just go sideways and don't bend at all. So as a designer, we actually had complete control over whether we wanted to have the system sort of bow down or if we wanted it to bend. So I'm going to show what happens if you do it the other way. So this is with the actual bend being back on with our current numbers for balancing. So like snap back up to where it was, and then it creates these chain reactions, which is more interesting to us than a system that was much more like Puzzle Bobble. But dampening off is what I meant to do, so let me go quick do that, and then I'll wrap up. So yeah, we have actually 2 drag values here. One is for when they're connected, one is for when they're free. So when they're free, they don't feel like they're really sluggish, and when they're connected, they start to be much more sluggish. And then actually, we have some of our values in script. I don't know if that's a good thing or a bad thing. So like these are actually hard-coded in the script. But it's pretty easy just to change these. And we never changed them after that we set them up in the first place. So I think that will do it. Whoops. Yep. So this is with all the stuff turned off, all the dampening systems turned off. And you'll see that when you start to build systems, they'll just kind of like freak out on their own continuously. So we actually had control whether or not we wanted this to happen or not. But when you're designing your physics game, oftentimes this is what you get. And this is actually pretty benign. A lot of the times what usually happens is systems just start to explode. They start to move around a lot on their own, and they start to add energy to the system, and then you end up with stuff that just is completely unmanageable. So this we actually managed to make it so that even if you stack a bunch of stuff together, it doesn't, even without dampening, it doesn't really explode on its own. It's kind of interesting because then you can actually shoot through. And what's funny is actually, now when I play this, I think I might have balanced it so that it was a little bit too dampened. That's part of the thing with losing objectivity is that like there are some interesting things about having it freak out on its own that you can kind of like shoot around it now because it's kind of swaying back and forth. But anyway, done in 3 weeks with Unity thanks to physics. So let me go back to my slides. So to recap on variables, make sure scale is to world scale, and scale is done first. You should balance your mass numbers second. And then third, you should just basically fiddle with dampening on all of your joints. If you have a bunch of joints, fiddle with their dampening values, making sure that the system is stable, but it doesn't feel too sluggish or too simplified. And then do all these things based on state. Change dampening whether or not it's in the air, especially. Like if you have like a platforming game, you might want to have it more dampened on the ground, or change friction depending on certain things. So that was a lot to devour in 40 minutes or however long I went. So if you have any questions, I'm always on AIM. I'm always available via email. I'm Matthew on the forums. And thanks to OT/UT. People are already calling you that in the forums, by the way. It's totally going to stick. So any questions at all on physics? Like what you've tried to do in Unity and haven't been able to do, or? Yes?
What I find hard is the gravity aspect. For example, in the pirate game, I find the boxes to fall down not fast enough, but when I tweak the timing parameters, they often ruin other things. It's too slow.
Yeah.
So it's a little bit slow motion effect.
Yeah, we actually modified. Well, first, is your scale proper? Because if the objects are too big, scale might be a little, like, they'll seem to be more sluggish as scale goes up.
Yeah.
We actually modified gravity also in Sploom based on whether or not they were connected. So you actually can do that pretty easily just by, in fixed update, you can apply like a force against gravity, or even just turn off use gravity and then do your own gravity. So we've done that where we've made things fall a little bit faster, which is a little bit weird because in real life, it kind of approximates, air resistance, because in real life in a vacuum things fall at the same speed. Yeah. So you actually can approximate air resistance by doing a very small drag value, like a dampening value. Or the other thing to watch out for is if you increase drag, it actually, like if you have a drag of 1, an object comes to rest within 1 second, but it actually means that the object has a certain max velocity. Like it's really hard to get objects to go faster than a certain speed if they have drag.
It's not good to make it too fast also because it's a, in this case, a cartoon feel.
Yeah.
And make it too fast. We tested it. The players find it confusing, so we got away with it. But sometimes the scale is not proper.
Yeah, actually, usually when I make physics games, I make the scale a little bit bigger because I actually prefer having things be a little bit more floaty, a little bit slower for the players. Like in real life, if you were to drop this, from this high, you have like half of a second to catch it. But in a video game, you might want to have like a second to catch it.
Yeah.
But yeah, curious how you did some things actually. Yes?
Why would you increase scale instead of just decreasing gravity?
Well, this was actually because most of our projects before were done in Virtuals, a very substandard engine, and we couldn't do many of those things. But in Unity, you actually have direct, like in Unity, you can actually just set the velocity of an object and interact with like physics in a way that you couldn't do in many other engines that I've used. So yeah, that's a much better solution. Other questions? Yes?
In the example of Sploom that you used, you had a separate rigid body that you used to connect the objects. First of all, why did you decide to do that? And second, did you reuse the same object to connect all of them, or did you use different objects based on the state of where they wanted to go?
We used the same object. The reason we did it initially is I actually wanted the balls to collide with each other even when they were in a joint. And in Unity, when two objects are entered into a joint relationship, like I have this object and now they're jointed, they actually stop colliding. So one solution that Sam just told me to do is just make a third object that is a rigid body with no collider. So it's just basically like a point mass. And then I connected both the objects to that so that they would actually still collide with each other. But we actually ended up turning that off later. So at some point, we just ended up with a system that wasn't probably required. And it made things, what the nice thing was though, because we have this other object in place between the two objects, we actually can modify its angular drag or its lock rotation. So when I made it so that they actually don't rotate like this, that was actually changing the lock rotation on that object. So by introducing another object to the system, we actually had a whole new set of numbers to change, which allowed us to do some things, but also it did make things a little bit more convoluted. Because we had to make sure that that object is deleted, and that object now has the joints, and it gets a little bit weird. But yeah, it was the same object made for all of our levels. We have levels that have boxes and other objects in it it's the same one. Other questions?
I have a question.
Yes.
From the perspective of using the physics API, when is it appropriate to set velocity, and when is it appropriate to add forces and torques?
We've actually never set velocity. I think some people do it to clamp velocity. Like if velocity magnitude is over a certain value, then set it to the new velocity. But I think it's generally a bad idea to set velocity, especially continuously, because then you end up with stuff. I would probably set velocity if I were loading the state of something, like if I had saved the game at a certain point and I wanted to reload all those objects and then set them back to where they were, I would probably do that. But we actually haven't touched actually manually doing that yet. Probably don't need to. Well, I think that's it for me. Thank you for your time and it wasn't just a Unity 2.0 feature talk, so I hope it was enjoyable to you guys. Thank you.